final paper this afternoon is from the Kentucky Cabinet Laboratory. The title is C-14 Tracer Studies of Fischer-Tropsch Synthesis. The authors are Li Min Tao, H. DeBage, and S.Q. Bao. And I should, I guess, introduce Dr. Tao here for presenting.
Sorry for you guys. After a long day, you still have to put up with me. Well, me too. My English is no good. Okay, if you have any question you don't understand, just stop me and ask me. Okay. The topic of today is C-14 tracer studies of Fischer-Tropsch synthesis in a slurry reactor. Here are my colleagues, and we come from Kentucky Energy Center. Next. Fischer-Tropsch reactor, everybody knows, just CO hydrogenation. And let's put a very common way is this generally accepted mechanism, which CO can be dissolved on the surface and somehow form intermediate. Then it has two ways to go. One is go to the next higher hydrocarbon, or it goes through the termination step to form product. In here, X is the chain propagator. Y0 is the chain initiator, and Y is surface reaction intermediate. Okay, no, I haven't gone that far, please. I want to go fast, but not that fast. Thank you for helping me. The reason this mechanism has been generally accepted because when you plot carbon number versus mole fraction of each carbon, in a semi-log paper, you will get a so-called Anderson-Schultz Slurry plot. Okay, the slope of this is R alpha, which represents the Kp over Kp plus Kt. Next slide, please. Next slide. Usually, you will see there's only one alpha value. However, the real world is not that simple. Back a long time ago, people thought there may be more than one alpha. More than one alpha certainly implies there may be more than one reaction mechanism going on there. Okay, back in 1980, Professor Satterfield about this topic again, and he showed a lot of evidence. Here's one of his papers. Here he used the ASF plot, again, carbon number versus mole fraction in a semi-log paper. Okay, he found is that oxygenated compound just go straight line. Okay, olefin compound goes straight line. However, paraffin doesn't. Okay, somehow come to somewhere around C10, C11 is tilted up. All right, and which about the total fraction tilted up too. Okay, he assigned the first one is alpha 1 and the second one is alpha 2. What he's trying to say is there are two alpha values. And he implies there are probably two chain growths going on there. He's not the only one. There's another guy from Wojciechowski or something like that. In Canada, he presents pretty much the same thing. Olefin goes straight line, but paraffin tilted up somewhere around C10, C11. And the total organic compound you plot, ASF plot, you get this kind of shape. So now we do have a question there. Okay, we do think there's some kind of things happen which cause this change, but the people they did the work, they only think there's two alpha. They don't give further evidence. What we are going to do, we are trying to use C-14 isotope to find out what's going on. Is there really two alpha or not? Please, next slide. Okay, don't worry about those cracks around here. I'm going to concentrate this two plot over here. Okay. In here, somehow if we can find a way to add radioactive chain propagator over here. So every time you add one more in here, so here, for example, you only add one radioactive compound. Here you add another. So per mole-wise, when the carbon number increases, you will see the radioactivity will increase, right? Okay, this is one case. If you can find some chain propagator goes in there as a monomer, get in here and make it goes up. On the other hand, you can find some other compound either oxygenated or olefin or something, which let it can be swapped on the surface, then somehow it's transferred to form surface intermediate. Then from then on, just keep going, because you have no way to add more. You just keep constant radioactivity in there. Therefore, when you make a plot, you will find out carbon number versus carbon 14 per mole, just keep constant. Of course, again, this is a theoretical value based upon one alpha value. However, in the real case, it's more complicated. So it's not going to give you this kind of information. But based upon this knowledge idea, we're going to pursue further. Please, next slide. All right, our operating conditions like that, we get fused ion catalyst for united catalyst, and our operating temperature is 260 degrees centigrade, pressure is 100 psi. We operate in the slurry reactor, and our slurry is octacosine here. Next slide, please. Okay, here's our flow diagram. Very simple. CO hydrogen come in. If I want to put some radioactive compound, I just pump it in through this pump. In this presentation, I only give you the information about pentanol pumped in information. Okay, that means I pump in pentanol about 1% volume-wise percent into syngas stream, and come to the reactor, react and come out. We can collect the liquid sample by put some trap over there, or we can analyze all of them. Okay, depends what we need and what we want. Please, next slide. Okay, here's the spectra we got. Okay, this reaction is CO hydrogen with the C5 labeled alcohol. Okay, which this radioactive compound is labeled in the alpha position. All right, the top one is proportional counter spectra, and the bottom one is gas chromatin GC spectra. Okay, the area under the proportional counter is proportional to the intensity which carbon 14 you have in there. For example, this first peak is CO. Well, you don't expect when you put C5 alcohol there, you don't expect CO have some radioactivity. That's why it doesn't have radioactivity. Here, if you are interested, I'm going to answer that question later on. Let's concentrate on 5 and 7, okay? Because when you put C5 alcohol in there, you expect somehow C5 alcohol will chemistry then come into surface intermediate, then keep going through the chain growth, right? So you expect C5, 6, 7 have radioactivity. Yes, they do. Okay, they do have radioactivity here. The reason C5 has small is not it is small because I use attenuation, which is 5. Which is much higher than those. So now if I make a calculation, compare C5, C6, C7, and as C7 as a basis 1, then I found certain PC over GC means the radioactivity per mole wise. Okay. You will find, well, you can argue it's constant or it's decreasing. Okay, I don't want to argue here. Let's go to the next slide and see what's going on, please. Okay, last slide. I would like to say it's going down, but you can see, well, it's constant. Okay, fine. Let's see, look, this one. Here, the same thing again. We go to C8, 9, and 10. All right. See, the GC spectra, they are pretty much the same. However, the proportional counter, which shows the radioactivity, they does drop down, right? There's no argument about that. Please, next slide. Okay, if we keep doing this, analyze from C9 to C14 and so on and so forth, and here we plot CPM, certain count per minute of radioactivity per millimole, so on. You will find out somehow the radioactivity just keep dropping down. Okay, when the carbon number goes up, it drops down. Well, which is not what we thought. In our theory, C5 alcohol, you assume it's go back to the surface form intermediate. So expect it's keep constant, right? You don't expect go up. You should expect it keep constant. However, our experimental data didn't show that way. Okay, didn't show that way. So there must be something wrong happening there. Okay, that's the reality. That's ideal cases. So they don't fit. That's fine. Okay, now let's see. Another thing I would like to point out is olefin have much higher radioactivity than paraffin. Okay, I separate them and I found that olefin have much higher radioactivity than paraffin. Okay, let's add another thing here is the reason it dropped down. Okay, you can put it on the other way. The other way is there are some non-radioactive compound has been formed during the process. That's the reason why the radioactivity has been diluted. Okay, it's not the drug, it's been diluted. Okay, if you keep this on mind, you'll find out what we are going to see. Next slide, please. Well, there's a problem now. We try to solve this problem. We think about there's the possibility that it can cause the problem. Number one is the slurry accumulation because we use slurry reactor. Number two is a secondary reaction. A lot of people argued you have a slurry reactor there, you definitely have some secondary reaction, of course, yes, but secondary reaction will not give you the drug. If you want to ask this question, I will answer you that later on, okay? The mass transfer problem, yes, we do probably have mass transfer. I'm not going to argue this, but you don't expect the paraffin and olefin with the same carbon number have so much different mass transfer coefficient, right? You see the olefin is much higher than paraffin. Would you please go back to the last slide, please? See, olefin is much higher. See, olefin is on this side, paraffin is on that side. You don't expect the same carbon number. Olefin have much different mass transfer coefficient than paraffin. Okay, next slide. So that doesn't work. So there another possibility is double alpha value, which probably can provide us some information. Okay, let's go to next slide, please. Okay, let's first think about accumulation in the slurry reactor. In the beginning of the operation, we put C-14, which is octacosine, as our slurry, which is 99.9% pure. But after 20 days operation, we take a sample from the reactor. We analyze, we found only 90% of the slurry is C-14. The rest of them distributed like this sort of bell shape. Okay, this one goes as long as about C6 or so. I didn't plot. This one goes all the way to 70 or something. Okay, what this tells us is, start from the very beginning. No, I'm sorry. When you want to input your radioactive compound in the system, there's already some non-radioactive compound exist, right? Because we accumulate all those things, which have paraffin and olefin. Okay, so you definitely have some problem there. Would you please show next slide, please? The problem we face certainly is very simple CSTR. We simplify the problem, okay? At a certain point during the operation, we want to input a carbon 14, which is a step function, okay? But however, on the output, it's not step function. It comes out like this, the typical CSTR response, okay? During a certain time, you just integrate the whole thing over here, which is your response. Okay, next slide, please. Based upon the CSTR, we calculated the accumulation effect. Here, the theta is resting time, which I calculate based upon how much accumulation deposited in the slurry. And in this slide, which it tells us is, first thing I need to point out is 24 here is, usually we operate for 24 hours. That means the slurry reactor keep going for about 100 days, but during the radioactive compound, I only operate for 24 hours. Okay, that's why I integrate from beginning to 24 hours divided by 24 hours. Because in the final sample there, you collect everything, you just average them. Okay. In other words, if I put 100 millicurie of radio C10 hydrocarbon in my system in the beginning, toward the end of 24 hours, I only got 95% out. Okay, for C16 hydrocarbon, if I put 100 millicurie in there, radioactive in there, I only got 46% out. Okay, so definitely there's a certain dilution effect because of the CSTR. Okay, CSTR accumulated so much in the beginning, which you just cannot kick them out except you run really long time of radioactivity compound, which is expensive. Okay, and I'm tired. I cannot run 48 hours. I only can run 24. Please, next slide. Okay, based upon this knowledge, let's go back to our plot. First, let's take the same thing, olefin part. Okay, we make the same plot, the carbon number versus the CPM per mole. Okay, the reason I put log just simplify the case. The circle point is the experimental point, which I already showed you. Okay. When we put C5 alcohol in there, you expect there's a straight line, horizontal line, okay? But it's not. Why? Because there's some accumulation effect. So if I calculate and count the accumulation effect, we'll find out if based upon the straight line, it will fall down. See, they're very close now. Okay, so our experimental point and our calculating point are quite much the same. Or the other way you can see is this line will tilt it up, like horizontal line. Okay, next slide, please. So for olefin part, there's no problem. The simple thing is they just have some accumulation effect, which affect the radioactivity you detect in your detector. However, for paraffin, there's some problem there. The same thing, we calculate the accumulation effect, but which is far from the experimental point. That implies the experimental point has been diluted much more than we thought. Okay, so there must be some other effect which caused this drop down so fast. Okay, but you should bear in your mind is that effect is not going to affect olefin. Okay, it only affects paraffin. Next slide, please. Okay, so if we want to answer that question with, seems to me, I think about 2 alpha value. Okay, so let's examine my ASF plot first, the carbon number and the log mole percent of whatever. It looks pretty straight, but certainly it's not. If you pay more attention, you will see this is a straight line. Then come to here is tilted up, okay, and the breaking point is somewhere around C10, just like everybody else get. Okay, so that confirm our experimental is quite correct. Next slide, please. Okay, if I analyze this further, I found this is our experimental data. Olefin does go straight down, but the paraffin somehow come to here, somewhere around C10, C11, it tilted up again, just like everybody else does. Okay, what this implies to me is somehow we have something going on the surface which form different intermediate. One of them responds both for paraffin, olefin, and oxygenated compound, but another one just simply responds for paraffin, that part. Of course, you don't believe me. Well, I don't blame you. Let's go ahead and take a look what we can find out. Please, next slide. Okay, what I postulate, speculate is this. If my chain grows, I have 2 sides or 2 chain growths on the surface. One is this one like this, regular chain growth. You come to here, surface intermediate, you become olefin, paraffin, and oxygenated compound. Okay. Another one is this one. You only can form paraffin. Okay. Of course, you can argue why you only form paraffin. I don't know. Okay. But I give you some evidence. It is possible from paraffin. Okay. See, we put alcohol in there. Certainly, we put more than alcohol. We put more than pentanol. We put decanol and we put ethanol in there. All of them give us the same thing. Okay, only the paraffin drop much faster, olefin drop less. Okay, and the reason, think about that. If this one only can form paraffin, everybody knows it's very hard to go back. This process definitely is irreversible. In other words, whatever you put out here, you try to go back to the chain growth to form surface in the intermediate. It is very hard. Okay, that means if we try to put radioactive in this chain growth, no way. That's why the product over here doesn't have any radioactivity. The pentanol only can go in here, okay, from radioactivity over here. Of course, you don't believe me. Come on, let's go ahead and find out. Next slide, please. Let's go ahead and re-examine this graph again. I told you there are 2 chain growths over there. Okay, if based upon this knowledge, and I told you again, there's only one chain mechanism can form, can let the radioactivity goes in. The other one cannot. So what do you expect? You expect not all the product after C5 have the same radioactivity. If they have the same radioactivity, for example, C6, we assume C6 formed from C5. Okay, if all the C6 have the same radioactivity, well, you will say, yes, they come from the same surface intermediate, right? But now, take a look. Here's the C6 group, radioactivity. Here's the GC. Look at this guy over here. He doesn't have too much radioactivity, this guy, right? And this guy, I didn't do too much effort to try, but I think it's paraffin. And see, those things, they do have radioactivity, okay? They do have peak, they do have radioactivity. Come to here, see? This peak is small, but if it has radioactivity, it will show up. Those 2 peaks is not about the same size, but they didn't show anything. This peak shows something. What am I trying to tell you here is when you look at spectra carefully, you will find out they are not homogeneous. Okay, the carbon-14 in all the C6 or C7 group, they are not the same. They are different. Okay, why is different? The easy answer that I provide to you is they probably have two different reaction mechanisms. Okay, you always can say, no, I don't believe that. Let's go ahead and talk about it more. Okay, if what I said, you temporarily accept that one. I plotted again my ASF, okay? And here's carbon number. I only take about C-20. I can somehow deconvolute this ASF plot. I put these two curves. Of course, you always can deconvolute a curve into two curves, okay? And we assume this alpha 1 and this is alpha 2. All right. Alpha 1 basically responds for the light hydrocarbon over here. Alpha 2, the chain growth will form basic primary hydrocarbon. For example, I give to you a very simple example. Come to C-14, for example. Only 0.02%, only 0.02 fraction come from the alpha 1, but about 0.08 come from alpha 2, so they're different. If the chain growth only can go through this line, definitely this line has more compound, doesn't have radioactivity. That's why it has been diluted. Okay, that's one point. Let's go to the next slide. Okay, like I said, the last slide. Oh, please go back. I'm sorry. No, not that one. The next one. Oh no, the wrong way. Go further. Okay, here we are. Don't go too fast. I'm sorry. Sorry, this problem. Everybody wants to go home. I know. I'm sorry. 2 more minutes. I promise you, I will finish. Okay. Let's see. If we assume this chain growth is the one which oxygenated compound can get in, okay, and form radioactivity here, what do you expect? You expect when I add C5 over here, the amount will increase, right? You will expect amount of C5, C6, C7, C8 increase. Here will increase, but it's relatively less amount. So you will still see this line will come like this. Okay, the front end increase a lot, but the lower end is barely see any difference. Okay, next slide, please. Okay, when I come to this slide, this is regular CO hydrogen reaction. This is C5, 6, 7, 9, so on and so forth. Here is the pentanol added CO hydrogen reaction. What you find out here is we do see dramatic increases for C5, 6, 7, 8, or C9 you can argue, but if you compare these two, make this one smaller like this one probably just like that. So C9 does increase, but after that you don't see any increases. So that definitely implies the chain we add in there only responds for a certain portion. However, don't take this wrong. It's not that it cannot go further, just because the fraction over there is much less. Okay, so over here it's not prominent. It's not there. It's not prominent. Okay, now I talk so much. I still haven't explained why our paraffin radioactivity drops so bad, right? Okay, let's go to the next slide, please. This slide, what I did is I assumed the same thing. When I put C5 alcohol in there, I should get a straight line. First, I tilted it down by the accumulation effect, because we know there's accumulation effect. The next thing I did is, from this line, I know some of the chain will have 2 alpha value, right? One of the alpha value doesn't have radioactivity, so it dilutes my radioactivity. So I average them and calculate again. See, now you can see the lines fall on there. So I do explain my experimental data with a good experimental result. I'm tired. I think you're tired. Let's ask